Donc on va enchaîner avec la présentation suivante de Mayssam Jannoun. Peut-être que Julien, de l'INSA Rouen. Probabilistic Fatigue Damage Estimation of Printed Control Board under Random Vibration.
Good morning, ladies and gentlemen. My name is Mayssam Jannoun. I'm a PhD student at INSA Rouen, and I'm here to present for you a collaborative work under the title of Probabilistic Fatigue Damage Estimation of Printed Control Board under Random Vibration. This work was supervised by Awais Paniako, Elami from INSA Rouen, and Pounier from Valeo Power Training System. In this work, we have studied embedded electronic devices, and we are interested specifically in the reliability of their mechanical behavior. These systems operate often in harsh multiphysical environments, so they are subjected to many load effects, such as temperature, vibration, humidity, shocks, etc. And in this work, we have studied the effect of random vibration on a printed control board in order to estimate the vibration fatigue damage of an electronic component. The plan of my presentation, spectral analysis of random vibration, then vibration fatigue damage in two approaches, time domain and frequency domain. Then I'll introduce our industrial application with submodeling technique, fatigue damage estimation, and finally conclusion and perspectives. Spectral analysis of random vibration. When we talk about random vibration, it is a dynamic behavior that is represented by an equation of motion. The excitations here are a random signal that are represented by power spectral density, that is the fast Fourier transform of autocorrelation function. Why is it called power spectral density? Spectral, it is for the FFT, and power is for the power of the signal. So in the case of stationary and Gaussian random variable, it can be converted into Gaussian time series that can be written in function of the mean of the signal and two terms in function of the frequencies and signal magnitude. In case of linear study, the response of random load is also a random process, so the output PSD can be written in function of the input PSD and in transfer function. In case of stationary and Gaussian processes, we can benefit from the statistical properties of the PSD in order to estimate the vibration fatigue damage. In case of embedded electronic system, they should be designed in respect to shipping and operating PSDs that are defined in the specifications. Vibration fatigue damage. In this section, we have two approaches, time domain approach and frequency domain approach. In time domain approach, we need to use the stress time history response, so we can control the mean stress to be equal to 0 by Heck diagram, then calculate the number of cycles to failure by SN curve, then count the cycles by rain flow counting method, then cumulate the damage by a Palmgren-Miner rule. This scenario should be repeated at every achievement of the process by Monte Carlo simulations, and then calculate the mean of damage. Now let us compare this scenario with a frequency domain approach. Here we should use the spectral response represented by the power spectral density of the equivalent stress. So we will use the statistical properties of the PSD and the SN curve materials and coefficient materials in an empirical formula in order to calculate directly the mean of the damage. Many spectral methods were proposed in the literature. In this work we have studied, we have used two methods, single moment methods and Dirlik method. In single moment method, we calculate the mean of damage in function of one spectral moment. In Dirlik method, we calculate the mean of damage in function of 4 spectral moment and stress range. Now, the implementation of submodeling technique in this study. This technique was developed in static analysis and recently to be used and improved in spectral analysis of random vibration. And it consists about developing a global model with coarse mesh, make a section at the concerned area, and calculate the PSD of displacements at the cut line section. The objective here is to detect the critical zone. So we make a structural zoom. We develop a local model at this concerned zone with refined mesh. So we can apply the PSD of displacement calculated from the global model as boundary conditions in the local model. In order to calculate finally the PSD of equivalent stress and use the statistical properties of the PSD in spectral methods in order to identify the failure criterion and estimate the vibration fatigue damage. Now I'll move to the industrial application. It is a printed control board equipped of electronic components. So the objective here is to estimate the vibration fatigue damage of a solder joint. So we developed a finite element model of the printed control board with the aluminium electrolytic capacitor component in 3 dimensions. And for the boundary conditions, we have applied the fixation at the assembly screws, and we have applied the random vibration excitation defined in figure 4, the vibration profile defined in figure 4. We have applied the submodeling technique, and we have made a structural zoom on the AEC component. So we have performed a model analysis of the system and in order to identify the deformed model shapes of the system and the natural frequencies. And on the basis of this analysis, we have performed the spectral analysis of random vibration. Finally, to obtain the PSD of a stress component according to the von Mises quadratic rule in case of biaxial stress as per Prumot. Vibration fatigue damage estimation. In figure 5, we have illustrated an example of von Mises PSD stress in global and local model at solder joint. Please note that these results are still in amelioration phase, and we are still working on these results. We can see we have a coincidence in peaks at the eigenmodes of the electrolytic components with an SN curve solder joint properties B and C defined in this reference, and the load time duration of 30 minutes, we can calculate the damage mean and the standard deviation in the table of figure 6. According to Larsen et al., single moment method is the most efficient method, and uncertainties can vary due to SN material properties. Now to compare between these methods, the time domain method. In time domain method, we can calculate the damage mean and the damage standard deviation. In spectral method, we can calculate only the damage mean. In time domain method, combined to Monte Carlo simulations, we can apply this method in case of non-stationary and non-Gaussian processes, that it is not the case in spectral methods. For calculation time, if we spend 2.5 hours for time domain method, we need the 0.2 seconds for single moment and 0.75 seconds for delay. To conclude, we have presented the methodology of assessment of vibration fatigue damage by 2 probabilistic methods, rainflow cycle counting combined to Monte Carlo simulations, and 2 spectral methods, single moment and deer leak. And we have applied this methodology on an industrial application, and we have improved in our application that single moment represents the most efficient method. The inconvenience of a spectral method that they are based on the linearity and the stationarity of the process. In the perspectives of this work, we are working on the improvement of submodeling technique and on the comparison of numerical results with experimental tests. Thank you for your attention.